Okay, students, so we're following inverse functions and we're trying something a little bit different today. We're making a video, so we're going to go right to it. And if it goes too fast, you can always rewind it. You can always rewind the stream and see and go back so you can go at your own pace. So, first we're going to look at an inverse relation. So, normally, relations are a relation between two variables. The relation is going to have an ordered pair. AB is going to be a relation if and only if the ordered pair BA is in the inverse relation. Okay? So that's the definition of an inverse relation. So let's look at the example because the definition isn't as clear as the example. So if the set A is input -1, output 0, input -7, output 2, input 4, output -2, and if set B is the inverse of set A, then the inputs and the outputs are going to be switched. So 0 as an input would produce -1, switching the inputs and the outputs. 2 as an input would produce an output of 7 because the inputs and outputs are switched. And then -2 as an input would produce 4 as an output. So with an inverse, the inputs and outputs switch. Inputs and outputs switch. Alright, so let's look at an inverse graphically. Y is equal to x squared. So we'll have a critical value, let's say I have 0. 0 squared is 0. And now let's look at our different numbers. -1, sorry. 1, -1 squared is +1. Get rid of that negative sign right there. 1 squared is 1. 2 squared is 4. And 3 squared is 9. But -2 squared is also 4. And -3 squared is 9. So when we plot our points, we're going to have 0, 0, 1, 1, 2, 1, 2, 3, 4, and 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that goes all the way off the screen. And we have the same values on the flipped side of the y-axis. So the parabola is going to look like that. So that's going to be the black function is going to be this function, and then to find the inverse of this relation, we just switch the x's and the y's. So we're going to do this in red. So here, 0 and 0, the x's and y's are switched. But here, 1, 1, once again switching the x's and the y's. But here, 4, 2, we switch the inputs and the outputs. That becomes, instead of 2, 4, we get 4, 2. Instead of 3, 9, we have 9, 3. Switching the inputs and the outputs. Instead of -1, 1, we get 1, -1. Instead of -2, 4, we have 4, -2. Instead of -3, 9, we have 9, -3. So let's plot the points. 0, 0, the same. Then 1, 1 is the same. But 4, 2, 1, 2, 3, 4, 1, 2, and then 9, 3. So we're going to have to do 1, 2, 3, 4, 5, 6, 7, 8, 9. So off the screen, 1, 2, 3. Then we look at the negative numbers. We have 1, -1, 4, -2, and 9, -3. So this is the inverse of our relation. And this is going to be coming up later. But notice, y equals x squared is a relation that is a function. And x is equal to y squared does create a parabola. This is a mathematical relation, but this is not a function because it fails the vertical line test. Fails vertical line test. So it's not a function. All right. Moving forward. Sorry about that. So we have y is equal to x squared and x is equal to y squared. And here we're looking at the inverse relations, okay? So it fails the vertical line test because the original function in A fails the vertical line test. So let's look at the vertical line test. So this is for your notes. A graph, a set of points x, y, in the xy plane defines as y as the function of x if and only if no vertical line intersects the graph in more than one point. So essentially, a function is only a function if a vertical line can pass through the graph at any point and only touch the graph once. So a vertical line, if we pass through here, only touches once. Here only touches once. But for this graph, a vertical line would touch twice, so it's not a function. The horizontal line test. This might be new. The inverse of a relation is a function if and only if each horizontal line intersects the graph of the original relation in at the most one point. So looking back at this function, the inverse of this parabola we know is not going to be a function. So this is a function. This is not a function. But we know that the inverse is going to be not a function because this fails the horizontal line test. Let's do a different color. So that fails the HLT. Because a horizontal line passes through the parabola and hits twice, which means the inverse is not a function. The inverse of this relation is not a function. One-to-one. A relation is one-to-one if and only if the graph of the relation passes both the vertical line and horizontal line tests. A one-to-one function is a function whose inverse is also a function. So only a function that passes the vertical and the horizontal line test is both a function and has an inverse that is a function. Okay, so which of the graphs in the figure above are graphs of relations that are functions and then relations that have inverses that are functions? So let's see. Graph 1 is passing the vertical line test on all parts. So we can say that we have graph 1 is good to go. Graph 2 does not pass the vertical line test, so graph 2 is a no-go. Relation 3 fails the vertical line test, so relation 3 is a no-go. And relation 4 is passing the vertical line test, so relation 4 is a function. So we have 1 and 4 for the relations that are functions. All right, let's look at part B, relations that have inverses that are functions. So these have to pass the vertical line test. So if the inverses are functions, this has to pass the horizontal line test. So if you look at this, you can draw a horizontal line at any point and it would only touch the function once. So once again, 1 is going to have an inverse that's a function right here. For number 2, well, number 2 is not a function. It will pass the horizontal line test at any y value. So if at any y value you can draw a horizontal line that's only going to go through the function once, that means that number 1 and number 2 have inverses that are going to be functions. Relation number 3 will fail the horizontal line test. Relation number 4 will also fail the line test. So we only have relations 1 and 2. So hopefully that helps you conceptualize your analysis. Which of the equations represents y as a function of x? Okay? So we have to see if these represent functions or relations, okay? So a is x squared plus y equals 1. So when you simplify this, you could just rewrite this as y is equal to negative x squared plus 1, and that's totally a function. This is a quadratic function. So we've seen these before. Quadratic function. For b, negative x plus y squared equals 1. This is going to be a little bit different. So you add x to each side. So you'll have y squared is equal to, add x to each side, x plus 1. And so in order to simplify y, you're going to have to take the square root of both sides. And so you'll have y is equal to the square root of x plus 1. All right. This is also a function, but it's a root function, but has a restricted domain. All right. The absolute value of y is equal to 4 minus x. So this is a situation where you have an absolute value function, but notice that the y is an absolute value instead of the 4 minus x. So this is a situation where, because this is not an absolute value of brackets, but this is not going to be y as a function as an x. All right, and then for problem D, x squared plus y squared equals 9. That's a circle, and a circle fails the vertical line test, so not a function. All right, maybe I'll go spend some more time explaining C later, but let's move on for now. All right, the graph of the relation you're shown is the relation a function fails the vertical line test? No. Does the relation have an inverse that is a function? Passes HLT, the horizontal line test, so yes. Is this function 1-to-1? Well, passes the vertical line test. But it's going to also pass the horizontal line test. So that means that the function is 1-to-1. Moving on. All right. The inverse of the function can be found by switching the x and the y values. So you have to switch the y and the x values. So you switch the x, y values. All right. Then you would solve for y. Solve for y after you make the switch. All right. Two functions are inverse, then they're symmetrical to the line y equals x, so that's just the standard linear identity function. And the notation for the inverse is f to the negative 1 of x. So that's not f raised to the negative 1 power. That means inverse. All right. So let's do some example problems. Find the equation for the inverse of x if f of x is equal to x plus 1. So step 1, switch f of x with y. So when we do that, we're just going to write y is equal to x over x plus 1. All right. Step 2 is to switch. Sorry, that's x plus 1, so not a y. Step 2 is to switch y's and x's. So we'll have x is equal to y over y plus 1. All right, step 3 is to solve for y using algebra. Solve for y using algebra. So in this step, let's look at the steps. First, we multiply each side by y plus 1. So we'll have x times y plus 1 is equal to y. Then we can distribute the x, so we'll have xy plus x is equal to y. Then we get all the y's on each side and get the x by itself. So we can have xy minus y equals negative x. We can factor out the y. So y factored out of x minus 1 equals negative x. And then lastly, we divide each side by x minus 1. So you will have y is equal to negative x over x minus 1. All right? And so now that we've isolated y, and it's a function, you can write y to the negative 1 for inverse form. And you can finally, step 4, if inverse is a function, switch y with the terminology f to the negative 1 of x. So in that case, we would just rewrite f to the negative 1 of x, so that's the inverse notation, is equal to negative x over x minus 1. All right. Try to write small so I can fit that all in there. So that's the answer. That's what you write as your final answer. But that's where all the work is completed. Negative x over x minus 1. All right. So let's solve this equation. Y is equal to 2x minus 1 over x plus 3. So let's do this a little bit faster. X is equal to 2y minus 1 over y plus 3. Then we'll have y plus 3 times x equals 2y minus 1. Distribute the x. xy plus 3x equals 2y minus 1. Get all the y's on each side. xy minus 2y equals negative 3x minus 1. Then factor out the y's, so you'll have y times x minus 2 equals negative 3x minus 1, and we're going to finish the next step at the top, but you will isolate the y by dividing each side by x minus 2. So y is equal to negative 3x minus 1 over x minus 2. So the inverse of the function is going to be equal to negative 3x minus 1 over x minus 2. I also want to note that you can also write the inverse of this function as positive 3x plus 1 over negative x plus 2. So that's just multiplying by negative 1. That's still the equivalent term. So that's something to know for multiple choice tests. Alright. Show that the cube root of x plus 3 has an inverse function, that's spelled, and find a rule for f to the negative 1 of x. State any restrictions on the domain for f and f of negative 1. Alright, so this is a problem that I want you to try by yourself. And then we will cover this in class. Cover in class on the board because I want you guys to share. Alright, so we're doing a little bit of mixed video lecture, non-video lecture. Alright, and then we'll have the inverse composition rule. So a function f is one-to-one with every inverse function g if and only if f of g of x is equal to x for every x in the domain of g, and g of f of x is equal to x for every x in the domain of f. So to verify these are inverse functions, we would have to take the composition of both. So f of g of x would be 1 over x minus 1 plus 1 over 1 over x minus 1. And so it's going to get a little bit messy, but multiply each side by, you multiply that 1 by x minus 1 over x minus 1 to get a common denominator. So you ultimately get 1 over x minus 1 plus x minus 1 over x minus 1 all over 1 over x minus 1, so that's going to get us x over x minus 1 over 1 over x minus 1, and that can be written as just x over x minus 1 times x minus 1 over 1. The x minus 1's cancel out. This becomes x over 1. So f of g of x is equal to x. So the functions are inverses of each other. Now, I want you to try g of f of x by yourselves. All right. Have a great day.